think the basic, why don't you start by introducing yourself, Bob, and then I'll
Sure.
come through, and then we'll perhaps talk about what we're doing.
Sure. Am I on camera now? It's rolling, is it? Okay, I'm Bob Hudgins of the Department of Chemical Engineering, even though I'm sitting over here in chemistry for this interview, University of Waterloo in February 1989. And unaccustomed as I am to putting my thoughts for posterity, we've been asked to talk a little bit about the history of cyclical operation in catalytic systems. And Pete, this is Pete Silveston. Do you want to say hello to the camera, Pete?
Yes, I guess I will. I'll say hello to the captain, also to Bert, who's behind, who's operating the system, and point out that it's really not that bad inside this building, but I was too lazy to take my coat off. In any case, Bob and I began our collaboration when we both virtually arrived at the University of Waterloo. I think I was here a year or two earlier, and we discovered that we had common interests in chemical reactions and reactor engineering, and so we decided to pool whatever money we could scrounge out of the Canadian government and our students and try and set up a critical mass or a team for work, initially really in reactor engineering, as we're not chemists. And a couple of years into this combined effort, we were sitting around the table, it seems to me, in similar circumstances, and Bob was discussing some work that he did in graduate school at Princeton, and it looked like we had an interesting area of research. It seems to me there was another incentive. We had run into people doing theoretical work, wasn't it? And at that time,
I think so.
Was Horn, did he visit us then and spend a half a year here? Or had we started before he came? I can't recall whether we started before he came or whether... Fritz Horn.
Oh, Fritz Horn. Oh, yeah. I think we had begun because we had Jeremian was here from.
Yeah, but remember that was the diluent gas effect.
That's right. That's right. We started really with playing around with the influence of diluent gases. Right. It was really during that we noticed how long it took for SO2 oxidation catalyst, a vanadium oxide, a vanadium catalyst, to recover back to its original activity, or I think it was really to come to a steady activity, and usually it wasn't the original activity; it was a higher activity, and we noticed that it was a function of the diluent gas, and this rang a few bells. I had by that time, it was 4 or 5 years after I'd finished my own graduate study at Princeton. And I had thoroughly decided that I would never again look at cyclical operation as I had tried at Princeton, because I felt that it would presumably show nothing. I was kind of jaded. So it was really that once we discovered that it took 6 to 12 hours to get to a steady activity, then the idea occurred to us that perhaps we should try to fool the catalyst while the activity was still high. Maybe we could feed it some other concentration, and perhaps some of this residual high activity would be maintained. We could get a net improvement in the overall process. So I think that was what...
It seems to me a number of things came across. Your own background in cycling, which you did as a grad student, and then some observations we made in the laboratory where we were trying to figure out why diluent gases affect the rates of catalytic reactions. And then I think the third factor that came in was that we had a visitor spend a sabbatical or a visit here who was undertaking simulation and theoretical studies on forcing systems periodically in order to get better performance. And I think at that point we decided, well, let's see what we could do in the laboratory. And since we had all the equipment ready for sulfuric acid or for SO2 oxidation, we just went ahead with that system, and it was one of the serendipitous choices because it worked out very well. There was a big effect, and it came in a region of the frequency spectra that was very unusual. The system was excited by very slow fluctuations in concentrations. And I think since then we've decided this is an area that people have been neglecting, and so we tried to build up a research effort in that.
Who was the visiting scientist?
Fritz Horn.
He was a theoretician. He's been dead for a number of years now. And he was interested in this probably for control systems. I think the whole idea was this bang-bang control. And they were developing mathematical theorems to describe bang-bang control. And I think he got into the area of chemical reactions and found out that when you put that sort of control onto a chemical system or to a paper model, a mathematical model of the chemical system, there was some improvements or changes that occurred.
Yeah,
So,
they talked about this phenomenon called the relaxed steady state or something. That was part
yes,
of it,
that's right.
wasn't it?
That was it. That was from their mathematical theory.
Right.
That simplified the mathematics. They
Yeah.
avoided differential equations. I could describe the system with algebraic equations. Now, we've never discovered it experimentally.
No.
It exists. It exists as a mathematical theorem or as a mathematical concept, fiction.
Yeah.
And but we've never been able to find it. It's a curious one because it says that if you disturb the system rapidly enough, you'll come to a very stable operating state. It's not the same as a steady state operation, and it's a state that probably should be should not be influenced by the speed of cycle. But we never see it experimentally.
Yeah, well, we can't cycle. You can't cycle fast enough in practice. Possibly that's the reason.
Yeah.
Because as soon as you get into rapid cycling, diffusion just averages everything out, and so you're essentially approaching steady state again. At least that may be a practical limitation of the thing.
Mm-hmm.
But even before this, I was kind of fascinated by, as a grad student, by the possibility. Because when I went to Princeton to study with Dick Wilhelm, who was the chairman of chemical engineering there, he was onto a sort of a cycling jag at the time, which was really the birth of this series of processes that he entitled parametric pumping. And he was always interested in catalysis, so he was looking around for somebody who would be interested to just get messing around in the lab with reactors under cyclical operation. And I guess I was a guinea pig. And we had a number of discussions, I guess one or two, with Sir Hugh Taylor. In those days, he was still, well, he was retired at Princeton. I don't think he gave the occasional appearance in the labs. He showed up occasionally in the labs just to sort of, because I think he'd been the guy who hired Dick Wilhelm for the chemical engineering department back in the 30s. And so they were great old friends. In fact, I think they had sort of a tremendous long history. But whenever Wilhelm had a problem in catalysis, he always used to go over and talk to Sir Hugh about it. And so I remember being on one or two of these sessions, and they talked about time constants of reacting molecules. And it was all sort of over my head, but we decided it was probably a good thing to try something in the lab. And I guess we fastened on ethanol decomposition, which was, I think, too bad. It was an unfortunate choice, or dehydration, that was right. And I think if we had fastened on a reaction which involved two molecules instead of a unimolecular one, I think we might have found something kind of dramatic. But we really didn't find very much of great interest, except a kind of an interesting chromatographic effect of the reactants and products in the catalyst bed, in the sense that the ether that was produced, the ether wave, seemed to come out ahead of the ethanol which was going in initially. And that was kind of fun, but you could explain all this from a chromatographic point of view. But kinetically, there wasn't really that much of interest. So I was a bit jaded, as I said earlier, and I was happy to find a project which looked as if it was a better choice than the one I had selected for my own doctorate thesis, doctoral thesis.
Well, that was, let's see, that was in the early 70s, I believe.
Yeah, it was. I think
started. So we're closing in on a 20th anniversary of this research effort. And I think we've seen it grow from activities in a couple of labs, ourselves in Canada, a group first in Germany and now in Switzerland, and then another team in Russia. And I would think there are now several dozen perhaps, laboratories that are interested in periodic operations of reactors. We haven't had any commercial success. We don't have any processes even close to commercialization of that, but the Russians have done quite well. They've used a different type of periodic operation, but they appear to have a number of industrial plants in operation using that type of a system. There are some interesting ramifications for catalysis in periodic operation. It seems to be a very sensitive technique for distinguishing between mechanisms. I think most people are aware that if you cannot observe what's on the surface itself and have to sort of approach mechanism studies by a black box approach, you very frequently find that there are 3 or 4 mechanisms that each fully explain your experimental observations. And even when you continue and look at a dynamic experiment, which does a better job of distinguishing measurements, you're still stuck with competing mechanisms that equally satisfy your experimental observations. It seems if you now do carry out your reaction in a periodic fashion, you can find areas of resonance, that is, frequencies which stimulate the reaction or suppress the reaction. And they seem to be very specific in terms of mechanism. Not all mechanisms satisfy or have the properties that will give you this type of resonance. So I think the contribution to catalysis is just that we can distinguish mechanisms. What's that?